All right, I want to start off where we left off yesterday. We finished here yesterday talking about when we're talking about confidence level. Basically, what we're saying is if we don't know what the mean is, so we don't know mu, this is unknown, okay? But we're able to find some sample means, okay? So take samples and find their means and find and we know the standard deviation of the population. What we can do is say that we're going to be, let's just say 90% confident right now, that when we create an interval, that the mean of the population is going to be inside that interval. So when we say 90% confident, basically what we're saying is that we're going to look at 45% that direction from the mean and 45% that direction. So that's going to give me what we call the middle 90%. Okay, that right there is going to that attaches to a z-score. Okay, so we'll just call it z right now. This also attaches to a z-score. I'll call that z. Now the z-scores there are actually, the way we're going to find them is based off of that blue area and that blue area. So what we said yesterday was that this here, that red was our confidence level. And like I said, I wanted to be 90%, so 0.9. And because this is symmetric about the mean, normal distribution is, everything's symmetric. So this, we call this a left tail. It's to the left-hand side, and it's the tail end of the curve. This would be a right tail. Okay. We're going to say that we're 90% confident that our mean falls inside this red region. Okay, and that red region will be defined by our confidence interval. However, there's a 90% chance that it falls in there. There's a 10% chance that it will not fall in there. That 10% chance, we're calling that alpha. Okay, and that would be this blue area. That one and that one. It's cumulative, 10%. Okay, but because these blue areas total 10% and they're symmetric, we're going to divide by 2, so we get 0.05. So this area right here, this real dark blue area, is 0.05. And it is going to be marked, or it's a demarcation line here, by this z-score. So that z-score is attached to that 0.05. So we call the z sub alpha over 2, okay, which is essentially attaching this 0.05. So what we end up doing, and we use our chart a little bit differently than what we've been using it, we'll kind of reverse the way we use our chart, okay? Normally in our z chart, we were finding a z in this column, in that row, and basically matching them up. And that would have been our probability. Now what we will do is we'll actually go through and try to find in the table where 0.05 is, and then work back out and say, okay, well, what is the z-score that attaches to that 0.05? And that will give me that z-score, and it will also give me that z-score, and that's going to help us determine then what is this interval in which we're 90% confident that our mean is going to exist in. Okay, so that's kind of the nuts and bolts about what we're going to do here. But I want to derive our confidence interval formula that you're going to see and we're going to use quite a bit. Our formula comes from this. If you remember this is the z-score formula for working with sample means, okay, from the central limit theorem. So it's from the previous sections. We know the central limit theorem states that the sampling distribution of means, which is another way of calling it is the distribution of sample means, is approximately normal when sample sizes are chosen to be substantially large. And we said n had to be greater than or equal to 30. Okay, and we arrive at this formula for z-scores. So one thing that we need to know, obviously that's the formula for z-scores. It says, in addition, there's a probability of 1 minus a that the z will have a value between negative z alpha over 2 and z sub alpha over 2. Okay, so what that means, if I choose my confidence level, let's do it this way. So confidence level plus alpha should equal 1. Okay, so when I go confidence level equals 1 minus alpha, that 1 minus alpha is that thing right there. Okay, so if my confidence level is 90%, 95%, 99%, we're saying that that 90%, 95%, 99% are going to occur between these two values, which you're seeing up here in this image. Okay, so it says, remember, if we want 90% confidence, then alpha is 10%. Thus, 1 minus 10% is 90%. So the z, the opposite of z sub alpha over 2 and z sub alpha over 2 are the z-scores that determine the central 90% of area on the normal distribution. So those are the z-scores that will be the, I use the word demarcation, the demarcation lines for that central 90% in this case. Okay, so it leads to this formula. Okay, so these z-scores, so the z-scores for this have to occur, so all our z-scores for our 90% have to occur between that value and that value, okay, or that z-score and that z-score. So basically what we do now is take this formula and we're going to solve for mu. Okay, so if we're going to solve for mu, some Algebra 1 concept here. So all I'm going to do is multiply all three parts by this denominator. So I'm going to get the opposite of z sub alpha over 2. It's going to be then times sigma over radical n. If you remember what that is, sigma over radical n, that is the standard deviation of the sample means. Okay, if you want to write it as sigma sub x bar, you can. Those are the same thing. So we'll do that. Multiply the middle part by sigma over square root of n, so that's going to give me x bar minus mu. And then multiply the right hand side, z sub alpha over 2 times sigma divided by radical n. Okay, now like I said, I'm going to solve for mu. So now what I'm going to do is I'm going to subtract x bar from all parts. So let's go negative z alpha over 2 minus x bar is less than negative mu, and then we'll have z alpha over 2 sigma divided by radical n minus then x bar. Okay, so right now we've isolated mu, but now mu is negative, so we're going to multiply everything by a negative 1, so this turns into positive z okay, this is going to turn into plus x bar. Now if I multiply by a negative, then that means the inequality sign changes directions. We have mu, inequality changes directions, and now we have negative, because I'm multiplying everything by negative, so this can be multiplied by negative, so negative z sub alpha over 2. And then we're going to have, let's see here, sigma over radical n plus then x bar. So now I'm rewriting everything. Basically, I'm going to flip everything or reverse everything so that I've got the correct order of my absolute or not inequalities. So this is going to be, so when I flip this, this is going to come first. So I'm going to write x bar, so this one's going to come first, minus then z sub alpha over 2 sigma divided by radical n. Okay, I'm going to flip this, gives me mu, and now this one comes last, so I'm going to write it as x bar plus z sub alpha over 2, and then radical n. Okay, so what we get here, remember yesterday what we talked about, is that x bar was a point estimate. X bar is a point estimate. Okay, it's a sample mean. And we said that the sample mean is rarely, if ever, identical to the population mean. So I think we did an example about the cars, like the mean price of 15 cars. Maybe we find the mean price of being 15 or $25,000 of those 15 cars. I would argue that it's probably pretty close to maybe 0% chance that of those 15 cars, any one of them is exactly $25,000. One, a handful of them are going to be above 25,000, and a handful of them are going to be below 25,000, and then they're going to average to give me 25,000. Okay, so a point estimate is just one singular value that is maybe not really going to be the best estimator for the population mean. But if we add a margin of error, maybe of $1,000, say, okay, well, my mean average is, or my population average is between 24,000 and 26,000. So we had $1,000 error or margin of error. That margin of error of $1,000 would ultimately be found right there with that information right there. These things that I highlighted in blue are the margin of error that we see when we say plus or minus something. Okay, like a point estimate plus or minus something. So up here, I think we did this example here where I did mean ages, and I said 27.3 plus or minus 0.4 years. So 27.3 is our point estimate. That's x bar. This 0.4 then would have been found by taking z sub alpha over 2 times sigma over radical n. Okay, and that generates an interval for us that allows then for a particular confidence level to exist. Now, what I want to do is talk about, how do we find that number? What does that number mean to us? So the central limit theorem states that when sample size is large enough, that approximately 95% of the sample means fall within 1.96 standard errors of the population mean, okay, or 1.96 standard deviations of the population mean. So the following is a demonstration of where the 1.96 number comes from. Okay, so if we've got 95% is my confidence level, so confidence level is 0.95. Okay, mean, so ignore the numbers down here. I'm not really worried about those. I don't know that they'd be wrong, but let's just say mu is unknown. But we want to be 95% confident that we develop some interval of data values in which our mean will reside in. What we do then is say, okay, well, if 95% is the confidence level, that means that alpha is 0.05. Okay, so the 95% says that we're going to go 95 this direction, and we'll go, or sorry, not 95, that 40, was it 42 and a half this direction, and 42 and a half that direction. Okay, or sorry, 47 and a half. I'll be able to add 47 and a half that direction, 47 and a half that direction. So that gives me our middle, all the way out here. That would give me my middle 95%. Middle 95%. So this here would be the middle 95%, or if we're talking about area, it's 0.95 of the area underneath that curve. That means, so this area here that area right there and this area right here are going to total to be 0.05 because again it's symmetric. So if that area totals to be 0.05, then alpha over 2 is 0.025. Okay, 0.025. Now, to see where this 1.96 number comes from, what we're going to do is we're going to, so this area here is 0.025. That area there, 0.025. We're going to take our z table and we're going to try to find that 1.96 number from our z table. So, and I don't know if I've got the z table. I don't. I don't have it. I think this is for a different quantity. Let me go back to, let's see here, z table. So what we do with our z table, so instead, in the past, we were looking in the central limit theorem in section 6.1, 6.2, 6.3. We're finding an area by knowing what the z table is, or the z-score was. Now we're kind of reversing. We're going to find in this table an area of 0.025. Okay, so right here, 0.026, 0.025, 0.025 on the dot right there. And if I look at 0.025 on the dot right there, go over here, and we see it's negative 1.9. And we go up, it's 0.06. So if I put those two numbers together, the negative 1.9 and the 0.06, well, what does that give me? That should give me a z-score here. Gives me a z-score right there, which we're going to say is the z-score of alpha, or alpha, z sub alpha over 2 is equal to negative 1.96. Okay? Now, because things are symmetric, we can also say this here, this z-score, is going to be the positive 1.96. Okay? But we can also see that or find that by taking, so this is 0.025. So if I take the area of 1 minus 0.025 and look that up in the table. Okay, so let's go 0.975 would be right here. That's 1 minus 0.025. And if I go across, we see that that's a 1.9. And if I go up, it's a 0.06. So merge those together, and you get a positive 1.96 here. Okay. So what I want to do real quick, go back to, let's pick up with Desmos real quick to make the argument. In working with Desmos, we know that we can deal with a normal distribution. Normal distribution. Should do it that way. Let's make it nice. We'll find the cumulative. Let's go between negative 1.96 and positive 1.96. And what do we recognize? The area there is 95.95. So that's 95%. Okay? That's exactly what that z sub alpha over 2 is providing us right here. Okay, that's a 1.96. So the 95% of the sample means we get a 1.96. So when somebody says that they're going to want us to come up with a confidence interval of 95%, every single time that they use 95%, that number right there, z sub alpha over 2, and this number right here, z sub alpha over 2, are going to be this negative 1.96 and this positive 1.96. So let's kind of do the same thing then with the other confidence levels. Okay. says, thus we can see that the z sub alpha over 2 equals 1.96. We then will take this number and multiply it by the standard error of the mean, which is that thing right there. It's the sigma sub x bar that we've talked about, standard deviations of the means. And that produces the maximum error of estimate, okay, which is that right there. That's the maximum error of estimate, okay. Where if we go plus or minus with that, then that gives us our margin of error, or what we've been calling the EBM from OpenStack's textbook. All right, so I messed the notes up a little bit here, but it's not a big deal. Let's kind of clean this up. It says do 95% confidence interval. We already did that one, so let's change this and let's make this 90, not 95, but 90. So let's just wipe this away. Let's see if we can do it this way. Get that out of there, kind of. Get that out, get that out, and we'll change that. All right, so let's do 90%. So the confidence level is 0.9. Then that means our alpha is going to be 0.1. And then alpha over 2 will be 0.05. Okay? So that means right there that this yellow area, that central or middle 90%, is in the yellow. So that means that this area over here is 0.05. And this alpha over 2 area over here is 0.05 as well. So two numbers that we're going to look for, finding these z-scores, 0.05, okay, in this part of the table. So this is what this table was for. If I find 0.05 in here, it's right here, okay. We got 0.0505 and 0.4947. This one is actually closer to the z-score, but we see it's negative 1.6. Okay, and if we were really doing our due diligence here, and we're going to cheat a little bit here in a moment, we would do a process called interpolation that would actually give me a better decimal point than, and I cut this off, this is 0, 0.00, this is 0.01, 0.02, 0.03, 0.04, 0.05. So we're looking between these two. So we're going to find out negative 1.6 and then between those. So somewhere between negative 1.64 and negative 1.65 will be that z for, or the z sub alpha over 2 value. Okay. Now, like I said, we're going to use software technology here to help us do this. And this is something that you guys can do as much as you need to throughout the rest of the course when needing to find these z sub alpha over 2's. You can either use the kind of the intuition and the knowledge we just used with the graphing of the image and then coming and jumping to the table, or you can use these commands in these different programs. Now, using these commands is one thing because they're just going to spit out the answer to you. I need you to understand what they're spitting out. So this picture and the logic that goes into this picture is pretty important. Okay, so let's do this with Desmos first. Basically, what we're doing here, if you remember, we were this area was found by taking what we call an integral. If I want to find the z-scores that attach that area, we actually have to do what we call the inverse of that integral. So what we're going to find out here, I don't know if let me just, let's hide that for now. To find this, we're going to actually have to type in inverse. This is the messiest command. So CDF standing for cumulative probability function or cumulative density function. Um, with this, we have to type in inverse CDF, and then we type in what distribution we're trying to find the inverse of. So we're trying to find the inverse of the normal distribution. Okay, and you could put you put 0, 1 in there. 0 meaning the mean and 1 being the standard deviation. But if you don't want to do that and you just want to do that, it should be sufficient. Um, Before we finish this off, let's go back and talk real quick about what's actually happening here with the table. Remember, the table, the direct way of dealing with a table was to find the z-score first. So maybe I want to find the z-score of negative 0.23. So I'd find that negative 0.2 and then the 0.03, and I would see where they intersect. What we're doing now is the inverse of that. We're starting in the table and working our way out to the z-score. So that's what the inverse means. It's kind of undoing the original procedure, or going maybe in the reverse order in this situation. So now inverse CDF, normal distribution, and then I have to type in comma what probability I'm interested in. So we're interested in a 0.90 probability. Okay. Actually, I'm sorry, not 0.9. What we have to type in the alpha value, the alpha over 2 in this case. So alpha over 2 would be, what was it, 0.05. So there you get the negative 1.644 number, which is consistent with what we said we should be getting, something in between negative 1.604 and negative 1.605. But this is a much more accurate. If we do the same thing with inverse CDF of the normal distribution, if I want to put, like I said, 0, 1, you put that in there, it's fine. And then if I go like 0.95, you're going to see that gives you the positive 1.64. So when somebody wants a 90% confidence interval, a 90% confidence interval, that is the, so 90% is the 1.644 number. And we'll talk about, how we use rounding. We use 1.64. We go 644. 95 we said was plus or minus 1.96. Okay, so let's see what 99% is. So let's use Excel to do this. Excel, all you have to do is you type in, let's see here, we're going to hit equals, and we just go type in norm inverse, or inv, norm inv, and when I hit parentheses, you see it asks for probability. So in this case, again, I believe it's asking for that cumulative probability, so I'm going 99%. So if we're going 99%, back up to the picture, 99%, so our alpha would be 0.01, and then half of that would be 0.005. So I'm going to type in norm inverse 0.005. The mean, because this is a normal distribution, so I'm going to just say 0 and the standard deviation is 1. If I hit enter, you see I get that number right there. Okay. If I go norm inv and then say, okay, I want the z sub alpha over 2 that's to the right of the mean, the right tail is what we refer to that as. I'm going to be looking for a probability of 0.995. Okay. 0, 1, and we see the 2.578, or 5758. So what happens is they usually round this one up to 5.8, 2.58. So a z sub alpha over 2 for 99% we say is 2.58 plus or minus. Those are three things that you might want to commit to memory. So I should say, I don't know, I typed this out very well. It says may be useful to commit these scores. We should say to memory right there, as they are the most commonly used confidence levels. But you can use any confidence level you want. You want to be 80% confident? We can do that. Okay, we just got to find out the tails, alpha over 2 stuff. Go to our table, go to our technology, and see what is the z sub alpha over 2 that goes with 80%. TI 8384, if you're using that calculator, I'm going to use that too much just because I think there are better things for us to use. But if this is your go-to, you can actually hit second, and you see where it says distribution here, DISTR, hit that. And we're going to come down to inverse norm. Looks different on other calculators, so we just kind of mess around with this one and see. So the area that I want would be, let's go with this 90%. So I'm looking at that left tail, so I want 0.05. That's all fine. Hit enter, 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 paste. So the command that I type in, so a lot of your calculators might not have that interface where it asks me for those things, and you would just type them in like this. So you hit inverse norm on like the TI-83 that is not a color version. It's just going to type in inverse norm. This is what you're going to see right here. It's going to open a parenthesis, and you got to type things in. First thing you type in is the probability, and then your mean and the standard deviation. And I want to say that even if you just type in your probability on those calculators, you're going to be fine. But I hit enter, and you see that the negative 1.644 number shows up. Let me go to classic mode here and see if that command does anything different. So again, second distribution, come down to 3. Yeah, it does the same thing. Okay, so and I don't have the different ROM on here to show that, but if you're going to use this calculator, it's not, like I said, it's not much different. What's going to happen is it's going to say INV norm, open a parenthesis, and I think on the older versions, all you have to do is type in 0.05 and hit enter, and it will give you that, because it's assuming that your mean is 0 and your standard deviation is 1 when you're using that command, so you don't need to put those in. All right, so an example of this. All right, we're just going to do one of these and cut this short, and then tomorrow come back and finish the rest of them. So the researcher wishes to estimate the average amount of money a person spends on lottery tickets each month. So they sample 50 people who play the lottery, found the mean to be $19 and the standard deviation to be 6.8. So find the best point estimate of the population in the 90%, 95%, and 99% confidence intervals of the population mean. All right, so when it says find the best point estimate, it's this right here. Okay, that's my X bar. That's my sample mean. Okay, 19 bucks. Okay, that is my point estimate. But it's likely that none of these 50 people, any of them, spent exactly 19 bucks. So, is that a good estimator for our population mean? Okay, we can get a better understanding of our population mean if we construct this confidence interval. Okay, so what we're going to do is we're going to say X bar plus or minus. So I should say plus first. So X bar plus Z sub alpha over 2 multiplied by sigma over root n is less than mu is less than x bar. I got this backwards. This should be a minus sign. Plus alpha over 2 sigma divided by root n. Okay. The one on the left is always the minus because if this is going to be a between statement, this number needs to be smaller. This quantity here needs to be smaller than this one, so that's why we've got the subtraction. But so we're going to go 19 minus, okay? So we're going 90%. That's the first one I want to do. So 90%, that attached itself to the z sub alpha over 2 of 1.644. That was the z-score. So minus 1.644. Okay, the standard deviation, we know that. We said the standard deviation was 6.8. So 6.8 right there. Divided by root n, n being the size of my sample, 50 people. Less than mu, less than, now I'm going to do the same thing. X bar is 19, plus then, essentially this thing right here. So when we do our, everything needs to be symmetric. Everything, this mu is going to be centered between this value and that value. So my margin of error needs to be subtracted, or my EBM needs to be subtracted from 19, but then also added to 19. So we get something like this. Okay. Some people will actually just come to the side, instead of writing it all out like this, they will just find out what is z sub alpha over 2 times sigma over root n. They'll figure that out to be, just this thing here. Then they'll add that to 19 to get the upper bound. They'll subtract it from 19 to get the lower bound. However you want to do it, doesn't matter to me. So let's calculate that real quick. All right, so negative 1.644 times, we had sigma of 6.8 divided by square root of 50. Okay, so I'm just going to put 19 there. So this is my lower bound. Okay, I'm going to find my upper bound by just cutting and pasting this, and instead of subtracting this, we're going to add this. So what we're saying now is that we can be 90% confident that our population mean, in regards to the average amount people spend on lottery tickets in a month, we're 90% confident that that occurs between a dollar amount of 17.4 and 20.58. Okay, it's a better analysis, or a better, I'm going to say, interval than the point estimate. If I want to view it a different way, basically what we're saying is, if you were to take these 50 people and sample them over and over, basically a different sample out of the population, but sample sizes of 50, and keep sampling them over and over and over and over again, 90% of those times that you sample, so let's say that we sample, we take 50 people out of the population and we do it 2,450 times. Okay, so we take 2,450 different samples of 50 people. What this 90% confidence level is saying is that 90% of those, so 0.9, basically we're saying of those 2,450 different samples, 2,205 of them would fall between, their mean would fall between those two numbers, or would be inside those two numbers. Okay. So that's kind of maybe a little bit of an introduction for developing confidence intervals. The entire process, guys, I don't think you're going to really struggle with this here. Okay. But I think this makes more sense if you understand why we're doing it, where the formula comes from, where these numbers of 1.96, 1.64, 2.58 come from, which I think that is the more important aspect right now, is understanding that logic and the mathematics that kind of underlie the work. Um, I think that's more important overall right now than just being able to do the calculations, get these numbers, and maybe not know what those numbers are telling us.